We at PQI are delighted this year to welcome Chris Monroe to give our public keynote. Chris is over there. Chris is the Jehuli Family Presidential Distinguished Professor of Electrical and Computer Engineering and Physics at Duke University. And he's previously led groups at the University of Michigan and at the University of Maryland. He's also the founder of IONQ, a company that uses trapped ions to produce quantum computers. The word pioneer sometimes gets overused, but Chris has been trapping atoms and ions since long before many of us were even aware that that was a thing. He was a PhD student in Carl Wieman and Eric Cornell's group at Boulder, and then subsequently in David Wineland's group, two well-known Nobel Prize winning research efforts. He's the recipient of many awards, including the II Rabi Prize in Atomic and Molecular and Optical Physics from the APS. And he's a member of the National Academy of Sciences. And I can think of no one better to give a lecture on quantum computing in academia and in industry. So let us welcome Chris, please.
Okay, very good. Curtains are closed, so if there's nasty questions, I can't easily jump out the window now. But okay, so welcome. It's a pleasure to be here for this venue. I see most of the crowd that was here in the day, but there must be some extra public. So I will. There will be some very high level comments here. Thank you. But I'll also put material in there that is appropriate for this conference itself. And I do want to cover, when possible, what I see as an interesting divide in the way academic research and industrial engineering happens. And I was just talking to Mark Schreiner a few minutes ago. It's actually very fun that quantum computing, quantum information science, is one of the only fields that it really can't be tackled by either one of these communities by themselves. And so it's created some interesting divides sociologically on how we report things, as you know. And I think in the US, this field is funded much more by industry than by government, which is kind of interesting. I think the government's a little nervous about that. They want to know what's going on. For good reason. We know that one of the known applications of a quantum computer will impact cryptography systems, future security. This slide, I wish I had more information on the period of these numbers, but these are the budgets of many countries and continents across the world whose governments are funding quantum computing. This is already a few years old, and I believe these numbers are probably a 5-year integration. I'm really not sure. But I guess the key thing to point out is that the US government is probably putting something like $1 billion a year into this field. And we've heard this figure from China, 25 billion. I don't know if it's published anywhere, but it's been thrown around so much, it's reproduced here. It's probably over many years, but it's certainly a concerted effort, and the EU as well. So it's we're finding. I guess I put this up because right now, even at $1 billion a year, industry is putting in much more per year in this field. So let me. You'll see what of my slides are sort of for business audiences and those that are for academic audiences. This one's a little bit of both. It looks very hyped that we have, human progress over time. We had the industrial age, the computer age, and the quantum age coming. It sounds hypey, but there's no absolute marker on the time zone, on the time limit here when we're going to make that transition. And one thing I think we can probably all agree on is that there are problems out there that regular computers are not only bad at, they will never solve. And these are the problems, of course, that have exponential complexity, and at some point there's not enough space to have computers solve these problems. Now, that said, we have very wonderful classical approximations for many of these very important problems, but there are others out there that we don't even think about because they're so hard. We just don't do it. So I think this is not a hype statement, and that is, if we are to solve some of these problems, it will have to be a quantum computer or something similar or more exotic. And it's because of the vast space that quantum systems give you access to. But it's very subtle, and I want to talk a little bit about how that goes and why industries are buying into this future where at some point they're going to have to pivot. So you've probably heard many announcements for breakthroughs, especially on the hardware side, and especially from the big companies. And these announcements I don't quite understand. The big companies, the big compute companies, are wonderfully investing in this field, and most of us in academics we've sent one or more students to these big companies. They're raising awareness in the field for sure, but their devices so far, it's not clear. In fact, it's pretty clear, according to the physics we know now, that they won't scale to a utility where you could break interesting codes or do other problems. That's okay. They should try to scale up current models of computing and try to make them quantum, I guess. That usually means they have to be cold and so forth. So these so-called breakthroughs, you have to read that with a grain of salt. On the other hand, in industry, you don't worry about something that has even a small probability of being successful. Investors routinely put their money in something that has a few % chance of hitting it. As long as the odds are really big, they'll still do that. And I like to think it's not exactly comparable, of course, but in academics, when we publish a paper and we're pretty sure we think it's 5% that this paper is right, we certainly wouldn't publish. So we tend to be much more conservative in academics. This is how science goes. It makes perfect sense. But I think we should not confuse one for the other. The audience and the community and the investors that are contributing to this field, they hear different things. And so it can be very challenging in this field to go back and forth between those two audiences. And this has sort of been my life for the last 10 years. It's certainly been fun. So I'll tell you a little bit about that story. But again, because it's a public lecture, I presume you're here because you've heard about the presumed power of quantum computers. And we, in thinking about how to describe and even how to build quantum computers, it really helps that we have this unbelievably successful history of classical computing over much of the last century, the last 75 years. And we can borrow almost everything in terms of what it means to compute in terms of, say, bits that have definite states 0 and 1, in terms of gates that allow us to have bits interact to make adders, multipliers, and to compute anything. The concept of a universal family of gates that allows you to compute anything is something that transfers right over to quantum computing, but we have something called qubits, quantum bits. We have quantum gates. Now, fundamentally, a quantum bit, in physics language, it's very easy. It's a two-level system. It has two definite levels, generally, and can also store coherent superpositions of those levels. And that's where the weirdness comes in. We can sort of have a confused state of reality. A qubit can be in both states 0 and 1. And the important thing is the weighting of how much 0 and how much 1 there is a continuous number. And in principle, we can control that number. So the way I think about how you build a quantum computer from that very simple statement. Oh, I should have mentioned the most fun part. The superposition, in a sense, is not the weird thing. The weird thing is when you measure a quantum superposition, it collapses to one state or the other with definite probabilities. And, well, you end up with definite states, which is a good thing because we don't observe in real life superpositions of things, say in space and so forth. So there are those two parts of quantum bits that actually goes a long way to even defining the entire field of quantum mechanics. There's lots of other, sidelights and so forth, and a lot of mathematics, but the concepts are simple enough. And I think in the guise of building quantum computers and applying information theory to quantum, it's actually a little easier to teach the fundamental precepts of quantum. Okay, well, let's say what a quantum computer is then. It's many quantum bits that are thrown together. Hopefully they are not observed while we make superpositions and we do something called entanglement. I'm not going to really talk too much about defining what that is. I don't think you really need to. But I think of the evolution of quantum computing theoretically as at a very basic level as a good news, bad news, good news type evolution. So the good news is when you put lots of quantum bits together, the possibilities grow exponentially. And so a little jargon here. So this is a quantum state of 3 qubits. And if you don't know this notation, the lines and brackets mean that this is a quantum thing. It doesn't have to be a real number. It's a quantum thing. And the plus sign means they're in superposition. And these A parameters are the continuous weights I talked about earlier. And so with 3 qubits, there are 8 possibilities. And in principle, we can program these 8 numbers to be anything. And right away, we see that there's parallel processing, because if we compute something on this state, we've computed some function of 8 numbers all at once. We get 8 answers all at once with one turn of the crank. And so that's really good. I mean, 8 is not very big, but if you consider several hundred qubits, there are 2 to the power 300 states that you have to consider with 300 qubits. And 300 qubits is a pretty small chunk of matter. Could be 300 atoms, 300 electrons, 300 things. You have to have great control of them, and there are 2 to the power 300 coefficients that you have to control. So that's not an easy task, but we'd be able to compute 2 to the power 300 things at once. And that's amazing. That's where we get the idea that there are certain things that you could, I mean, that's an example. You could never do that classically. Never have access to 2 to the 300 of anything at once. Oh, thanks. Okay, so that's the great news. You would think that, oh, great, let's all make quantum computers. But of course, the bad news is you have to look at the system. You have to measure it. And when you measure it, as I said, you randomly get one of the answers. And if there are 2 to the 300 possibilities and you only get one of them, it's going to look like noise. Pretty much the probability of each one of these is 0. So it's really spread out. Kind of obvious, I guess. But the last subtle piece of good news is that before you make a measurement, these are the superposition is like a very complex wave, and we can poke that wave around to make interferences happen. And this is the art of the algorithm. These interferences are very hard to draw. Everything here is very hard to draw on a piece of paper, but these red dots are meant to note that we're interfering 2 particular states, for instance. It doesn't have to be that way. These red dots are called quantum gates. They allow us to, and they operate without measurement. And it turns out there exists algorithms, at least one, that we know exactly the prescription of gates that gives you an interference where almost everything cancels. What I mean by canceling is that they don't exist over here, and only one or a few, or maybe a few hundred, a small number that you can repeat the computation over and over again and get their distribution. And that distribution, or that singular answer, can in some cases depend upon 2 to the 300 inputs. Okay, so that's, I think, pretty much all quantum algorithms can be at a very, very high level discussed in this way. David Deutsch was really the first to show this final piece of good news, and that was in the early 90s. And then Peter Shor, we heard about his algorithm earlier. His algorithm in 1994 is the singular one where we have proofs where we know exactly how it scales. And I want to talk a little bit about that. The Shor factoring algorithm. So this is one, I mean, it's a class of algorithms, and it's a class that maybe contains only one algorithm, but it's hard to believe there are not many more, but you know, it's been 30 years and there are a few out there that we have. I suppose there's some esoteric ones that we have proofs for, but they're pretty few and far between. So factoring is in a sense, the inverse of multiplication. It's a lot harder than multiplication, and number gets big enough, it turns out to be exponentially hard. Well, if n is the number of bits to represent the number you want to factor, this is sort of how many steps or the amount of time it would take to factor that number on a classical computer. So this is called, I think it's called super polynomial. It's not exactly exponential, but there's no, it's slower than any polynomial. So it doesn't scale well. You might as well think of it as exponential. My life, that's I think of it as exponential. Shor showed that this is actually a polynomial problem now. Squared, maybe n cubed, and I'm not an algorithmist, but it does change the complexity class of this very important algorithm, factoring numbers. It's very important, of course, because the inability to factor is what underlies the security of most encryption standards. So it's a very important problem. How does Shor's algorithm work? Well, given the number 39 that we want to factor, or whatever the number is, that number defines where and when to apply these gates, these 2-bit and single qubit gates that are universal for computing. And I'm not going to obviously get into details on how that works, but I can show you at a very high level how Shor's algorithm works. Factoring 39, well, we're going to have at least 6 qubits, because 5 qubits will give you 32 states. 6 will give you 64. So that's enough, at least, to store the number. So we store a superposition of the first 39 numbers. And with that number 39, we come up with a schedule of gates and operations in space and time. And there's only n squared of them, which is important. It's not scaling exponentially. And this quantum state goes from that superposition to this superposition. Dang. I've used this slide for the last few years. The first time I used it was in front of Peter Shor, and I kind of looked at him and I said, "This is how it works, right?" And he nodded his head. So yeah, there's a lot of stuff going between here and here, including, crucially, you can't look. You have to manipulate this quantum system or this quantum computer without looking. Very hard. Okay, so that's Shor's algorithm. It really put the field on the map in 1995. And at that time, I was a postdoc, or actually a staff scientist at NIST, working on atomic clocks. I was entangling atoms to make better clocks. And it turned out we were making quantum gates for pretty good qubits. So this field sort of changed my career at a very young age. And yeah, back in the mid-90s. So while Shor's algorithm really started the field, I think it would be sad if quantum computers are only used to factor numbers. I think that's kind of boring. We can always change encryption standards. It may take a long time for society to do that, but then what? Okay, we can factor numbers. That just seems boring to me. Now, the good news is there's another class of algorithms, and I'm lumping all of them into one word, and that word is optimization. Good news is it pretty much hits every walk of life, every sector of society, both academic and industry. The bad news is you can't prove that it works. So these will be, academics hate this H word, heuristic. These optimization algorithms will likely be heuristic, meaning that they don't come with a proof. But a heuristic is okay as long as it works and you can verify that it works. So example here, what's the highest peak of this mountainscape? Clearly it's this one because you can see it. We can make a plot with 2 dimensions, latitude and longitude, and it's sort of obvious. But if this function, the topography, the altitude versus x and y, actually is a function of 10,000 variables, you can't plot it, and you certainly can't find the optimum. You'd have to search through exponentially many trials and save the biggest one or something like that. So that's an example of a typical optimization problem. The traveling salesman problem is the one that everybody knows. My daughter's a graduate student in math and computer science in Boulder, actually. And she works on heuristics. She has worked on heuristics that help the traveling salesman problem. Now, the traveling salesman problem, we want to visit a bunch of cities on a map, finding with the minimum path. That's like an energy function. You could imagine mapping that to a Hamiltonian and minimizing the Hamiltonian. So it really touches on quantum simulation in a way. The heuristic, by the way, is to break up the traveling salesman problem with 48 cities is actually not that hard. But if I give you 4,800 cities, forget it. You will never find, classically, you'll never find the minimum path. And the heuristic my daughter worked on for a while, I think it's a popular one, is to break it up into a bunch of smaller cells that you can solve it and somehow stitch. It takes a lot of care, but you stitch together those cells. And it's going to be a pretty good answer. And in fact, they do work very well. We think I don't know if we know that they work well. But you're obviously not going to go from Boston to Washington and to Florida and to Texas. You're going to heuristic laws that you'll follow. I've read that UPS delivery schedules, they don't make left turns so that they optimize the travel route. And you can see that's a general good thing to do, not make left turns, but you can see also where you might get stuck. Now, another class of optimizations, some people don't call them optimizations, I do, and that is molecular simulation. What is the conformation of a bunch of electrons on a complex molecule? That's more of a physics and chemistry problem, and I think that's sort of a separate class of optimization with respect to quantum computing because it's already quantum, and there are very efficient and more efficient maps of qubits and bosonic systems to these electron orbitals. And the poster child, I guess, for molecular simulation are these big nitrogenases that they break nitrogen into ammonia, which is a very important industrial product and so forth. But we don't understand how this works at the molecular level. And that's just, I think, touching the tip of the iceberg in this field, molecular simulation, that I think is probably one of the known big applications of quantum computing, but it will be heuristic. The thing about these optimization heuristics, remember, is that if you get a better answer than a classical computer got, then it's useful. You don't need a proof. That's the proof that it's useful. And this idea of a heuristic is something I think academics tend to frown at it because you can't prove it, and I guess that's fine. Somebody earlier today said computer scientists like proofs. I think Eddie, you said that, yeah. That's okay. In industry, you want things that are useful, things that'll make shortcuts. Okay, so let me now jump into, I've been postponing, how do you build these things? I guess the answer is it's really hard. These two rules I mentioned, being able to make superpositions while not looking, but then being able to look, I didn't mention that you need to be able to measure with very high efficiency. So you're sort of turning off the environment, and then you're not only turning on the environment, you're getting information out really efficiently. And that's really hard to do. So this is a summary of a figure from a review article that the editors of Science magazine published a long time ago, 10 years ago. I reorganized some of the columns in terms of two classes of experimental qubits. On the right side, what I call synthetic qubits. These are usually fabricated in solid state. That's why they're synthetic. Superconducting junctions are probably the most popular because a superconductor has very low loss, zero loss when it's in the superconducting state, and you can store information that way and read it out with electronics and so forth. And these synthetic qubits, a couple of comments, they're typically solid state. They usually have to be very cold to freeze out all the environmental influences and so forth. But even still, making identical qubits to scale is really, really hard. And those differences in qubits, they actually change over time. And the bigger the system, the much harder it is to even calibrate the system. So I'm not sure, I mean, there's a lot of cool physics that's going on in all of these platforms here at Pittsburgh as well. And I think that will continue to be the case for a long time. But I think in terms of a scalable quantum computer, it's going to need new physics, some kind of breakthrough in a new material that does something very cool, like having magically, this is the string theory of quantum computing, topological qubits, that there's somehow a degree of freedom that self-error correction doesn't have errors. It's theoretically possible, just like string theory, but it hasn't been clearly observed yet. On the left-hand side, we have what I call natural qubits. These have their own challenges, but it's not about fabrication. If you have an atom of a particular isotope, you can replicate it with perfection. That's why we make atomic clocks out of atoms of a given isotope. So having standards of time, turns out, confers to many advantages for standards in qubit design. So we have atoms, atomic ions, they're very similar. One has a charge, one doesn't. Individual photons, individual electrons, things like this. Individual neutrons, not so much, because you need a big facility just to make them regularly, and they're very fast. Photons are very fast as well. It seems like we need a memory somewhere, and that's why I think these two platforms right now are, I think, really the leading platforms for scaling going forward. That may not be true in a number of years, who knows? Okay, now the challenges on the left side is not, I would claim, it's not really one of physics so much. There's still some physics to be had, but we're not going to get all that much more understanding about the atom, even though we can isolate it really well. The challenge here is how do you control, how do you get a single atom to not be part of a solid, to suspend it? We heard, I mean, Dave talked about laser-based traps, and Marcus Greiner as well, Guido Pagano talked about electric traps for ions. So we suspend them in a vacuum chamber. So there's a lot, there's a lot of, by now it's engineering. There's not really much physics in a vacuum chamber these days. But the challenges are clear because nobody's engineered that kind of a system before. Whereas with very large scale integration and the silicon tech that's gone on for the last many decades, one would hope you could simply scale up by printing more silicon transistors at the single silicon spin level. It turns out, I'm not sure how that will scale, but at least they don't worry about throwing numbers of qubits on a chip. They have to control them at the same time, and that's the real challenge, I would say. Okay, so I'm gonna clearly, you kind of know where I stand. I mean, obviously, I've been working in the atomic physics realm for many years. Now, this plot is a fun plot. There's some sociology here as well, which is rather interesting. But this plots the 2-qubit gate fidelity, the quality of entangling gates, which is generally the bottleneck to building quantum computers. How do you controllably entangle two particles, whatever they are? These three platforms, these are really the only ones that have been built into systems so far. Superconductors, neutral atoms, and trapped ions. As I mentioned, we got started very early with trapped ions, almost by accident. Some sociology here. Neutral atoms, all of the physics needed to control individual neutral atoms was sort of known 10 years earlier, but nobody really worked on it very hard. I think they were busy on other things in atomic physics. There was wonderful work in cooling atoms to Bose-Einstein degeneracy, and there's a lot of work in that field. And only in 2010 or so did people start thinking about controlling individual neutral atoms. And Dave is one of the few that really started thinking about how to pack them in tightly, how to control, even in 3 dimensions, how to focus laser beams on on exactly one atom in a 3D lattice. Now, this is over the last 30 years. This is the error. This is the log plot, of course, and the complementary fidelity. It's kind of a naive view of that. Now, you should take every one of these dots, points, it has a reference, but you should take these with a grain of salt because many of them involve exactly 2 qubits and no more, which doesn't necessarily imply they can scale, but at least it'll tell you that the physics is okay. A lot of the trapped ion work in particular was very small numbers of ions. Another thing you see is neutral atoms are really coming down strong. That's really exciting. So are trapped ions. These last 2 points come from industry. That should be telling as well. Whereas the neutral atoms, industry hasn't quite beat universities yet. I think it has to do with this 10-year gap, I think. That didn't help things. Now, you'll also notice, you might, and I wouldn't put much significance in this little bump up. In this last work, it's very hard to pull out individual gate fidelities in these big systems, but there are huge numbers of qubits. So it sort of makes sense that their fidelity per qubit on average, or the median, will go down. So I would say the messages are the trapped ions need to start working on scaling, and they have to stop working on fidelity. And these superconductors should work more on fidelity and less on scaling. If you have 1,000 qubits, but they're only 99% pure when you make gates, you have way too many qubits. Have 2 qubits and you have 5 nines of fidelity. I mean, it's also a waste of time. You only have 2 qubits. So you have to think in the future. And of course, all these platforms people are thinking about both scalability and fidelity. But I wanted to tell you a little bit about trapped ions. I think the call right now is to scale them up to get many more of them in a system. So I want to tell you a little bit about that story. So this is a picture from my lab at Duke. we're fortunate to have a group at Sandia National Labs. This is the US Silicon Foundry. They make rad-hard chips, CMOS, and they also have some research groups that can do sort of whatever you want in silicon. They have an ion trap group there, a very good one, and they've made these very fancy chips. So this chip here, the bow tie looking thing is about 1 centimeter across. There's nothing quantum about this chip. It's just a platform to hold a bunch of electrodes. There are about 100 electrodes. You can't see them here. You can see the wires though coming into them. And these atoms float above the midpoint of that bow tie by about 1/10 of a millimeter. They have exactly 80 atoms, 80. They're all 171 ytterbium. This is the atom Guido spoke on earlier. How do we know that? Because we're shining laser light on them at a particular wavelength that we know to about 8 or 9 digits, and the ytterbium atoms fluoresce in a very narrow range. When we turn the light off, the atoms are still there. We don't really know that directly. We have to turn the light back on to make sure of that. The left to right distance is about 1/2 a millimeter, so they're separated by a few microns. They're obviously optically resolved. We're just collecting light on a camera here. Another atom, barium, emits in the green, and you can see a single atom with your naked eye if the room lights are out. And it's because these atoms are very special. They fluoresce very strongly. Atoms are also very cold. They look kind of fuzzed out here, but that's entirely due to the optics. It's almost diffraction limited optics. So just like the resolution of stars at night, we're going to be limited by the aperture that we're able to collect. The atoms are so cold, they're maybe, I don't know, 100 to 1,000 times smaller than the blobs. They're real points. They're charged. I forgot to say that, my favorite part. They're charged. Maybe that's obvious because they're forming a crystal. You might call this a 1D crystal, but not in the sense that Dave talked about, because quantum statistics plays no role here. These atoms are distinguishable because their wave functions just don't overlap. We call them Boltzmanns sometimes. They're not bosons or fermions, but they're individually controllable and they're absolutely identical. They're really good atomic clocks. The hyperfine levels form the 2-qubit levels. And I could add a few more digits here. It's way more than we need, the sort of passive stability. So how does this look like a quantum computer? Well, when we turn this light off, we can turn other beams of light on that make this entanglement I mentioned. And it actually has to do with applying a straightforward force to the atoms. These atoms are separated by a few microns, but the force that we apply moves them a few nanometers. So it's just a tiny bit. But when just like a bunch of pendulums connected by springs, if you wiggle one of them, they all know about it. There's phonons that go through the chain and so forth. We know how to control that. So laser beams are what allow us to entangle. The laser beams don't scatter like this. They don't cause fluorescence. They're sort of, they're dispersive interactions. In this sense, the atom's sort of like an index of refraction, if you want. So there's a recoil and so forth. That atomic physics is very well known, developed in the 70s, 80s, and 90s. And so I'm going to show you a little animation how a very simple quantum computer algorithm might work. So what we have up here, the cursor's blocking it. This is just a 7-qubit circuit. This is space, that's time. And these 7 qubits are all prepared in the state 0 through something called optical pumping. That's what we're doing here with that laser beam. And then these blocks are gates that require individual focused laser beams that hit the target atoms. And you can see when they hit them, they move and so forth. You can do this in PowerPoint. So this is, I don't know what this program is, but it's a pattern of gates. It might be a piece of Shor's algorithm if you want to factor numbers. And so we apply gates or single qubit gates. They just like not gate on single qubits, multiple gates. And then at the end of the day, we make a measurement similar to the initialization step. And the qubits that are in the state 1, they glow. The ones that are in the state 0 are dark. It's sort of as simple as that. This is actually what it looks like in a trapped ion quantum computer. Now, if you step back and you look at a typical quantum computing lab, it's a mess because we have lasers and optics and fibers and power supplies everywhere. This is a physics experiment where everything is flexible and tunable because we're doing physics experiments. But over the last many years, we figured out how to kind of shrink things down, systematize things, do some careful engineering, try to freeze things that we can. Let's not make everything flexible. And in this box, about a meter cubed, pretty much everything you saw on the previous slide is in there. And the box is important because any air currents from the laboratory or temperature fluctuations actually affect things. Remember, we have these beams that are coming across that chip. And this, to make this box, it was very expensive, took many years, and we were funded early on by the intelligence agency version of DARPA called IARPA, and more recently by the DOE and the NSF to continue this at a higher level, run algorithms and so forth. And these grants gave us the ability to work with Sandia and a bunch of other industry concerns that could help us engineer products, not for CMOS lithography, but for poking atoms with the same types of laser beams. In fact, if you wonder why ytterbium, one of the main reasons is that the laser that we use for the gates is the same laser that's used for high-level CMOS fabrication, 355 nanometers. It's sort of a commodity. Now, here's the same picture of that chip. Jungsang Kim, my colleague at Duke, also co-founder of IONQ, he's very interested in little gadgets and little widgets, miniaturization and higher performance. He's figured out with cold quanta, which is now inflection, he's figured out how to seal the vacuum right on the chip itself. And the little ion pump's not shown, but it comes off one of these windows. The vacuum is remarkably good, even at room temperature, which I forgot to mention. This whole system is at room temperature. The atoms are cold, but it's at room temperature. So with a system like this black box, we can now do maybe physics and other types of science at a much higher level. It's what I call the quantum computer stack. And we first started thinking this way about 10 years ago because we have our atoms, they're controlled with lasers. We have pulse shapers that control the waveforms that go into the optics. Then at the top, we have an algorithm, a bunch of gates, and we have to sort of go from user to compiler to controller. There's a lot of computer science. There's a lot of ways to compress the number of gates so you don't have to use so many. To mitigate errors, errors are very structured in this system. When you leave qubits idling, there really are no errors. T1 and T2 are much longer than any time scale, including it's hours. It can be hours. So almost all of the errors, at least at the 4, 5, 9s level, are given by control errors. Laser noise, lasers that move in the breeze. So there are ways to, if errors have structures, you can artfully use those structures to compose gates and algorithms in the right way. These are also heuristics. It's not like active error correction, which is something we'll need to turn on at some point in any case. So in our substantiation of a quantum computer, this involves physics, AMO physics, engineering, computer science, and then pretty much anything. And we've been using these machines to do all kinds of things over the last many years. You're not supposed to read these, just except to note there's a lot of collaborators. They come and they would like to run a quantum simulation of interacting spins that are fully connected. Well, these qubits are effectively like spin 1/2 particles in magnetic fields. There's all kinds of kind of fun applications. Milli charged dark matter limits. I just saw that in the corner of my eye. You can ask me about that later. That's a little out there, but it requires great control of a chain of ions for very technical reasons. I want to talk maybe about a few of these on the physics side. So we in these same experiments, we can run quantum simulations. To me, the difference between a quantum simulator and a quantum computer is it's not super important. I think a quantum simulator is a restricted quantum computer, if you want to think of it that way. It's easier, of course. You don't need arbitrary control of the qubits. And it also informs us in science, especially, say, in condensed matter physics, even some in cosmology, for God's sake. So this is an example. On all of these spins, there's, I think, 21 of them, we were able to implement, this is what's called an XY model. It's a 2D spin flip-flop And the coupling is sort of like a couple of different icing couplings. And the couplings are alternating between weak, strong, weak, strong. And I guess I didn't know this up to a few years ago. This is a well-known model called the Su model. And it's one of the simplest models that admits edge states that should be that should be longer lived and excitations in the bulk. What do I mean by excitations? Well, this Hamiltonian allows a spin flip. It conserves the number of, say, spin up particles in the chain, and the spins can freely move along the chain with no energy cost. And it turns out if you create an excitation on the edge, it tends to stay there, whereas if you do it in the middle, it tends to dissipate. So these plots, time goes down, and this is the state of the 21 spins. And you can see in 2 through 5, we excited a spin, we flipped a spin in the bulk, and it sort of moved around throughout the whole chain, kind of dissipated. But the ones on the edge, they also dissipated due to laser noise, but they were much more confined than the others. So sort of a simple demonstration where and I think in the neutral atom community, they've also measured coherences across the left to right. We haven't done that in this work. That's important to note. And I think due to time, I'm going to probably skip over. This is one of Guido's papers many years ago when he was in my group, and that is this icing model with a transverse field can be mapped to meson and quark confinement and string breaking and so forth. There's a whole series of types of experiments that you can do there. Again, here, when you have a domain wall between ferromagnetically ordered spins, when you have a domain wall, that domain wall acts as a charge. When you have two domain walls, it acts as a meson. It's two charges, and in between is sort of the string. And how the dynamics of that system evolve when you put this Hamiltonian on, or even a more complicated one that has Ising couplings, as well as transverse fields. String breaking here, which is also observed in neutral atom systems. We're still waiting for this one to leave the archive. It's taken a while. But again, the important point here is we've been able to collaborate with people like Zore Dawoodi, who's a nuclear physicist, and she had to learn a lot about ion traps here. She's at the University of Maryland. Alexei Gorshkov's also at Maryland and NIST, and Orr Katz is now at Cornell. The last one, very quickly, this is a circuit. It's not a quantum simulation, but it's a circuit that implements a very baby version of a certain machine learning problem. It's called contrastive learning. Again, I didn't know what this was 2 years ago, but contrastive learning means that a system might be able to recognize, say, images. It doesn't have to be images, but it might recognize images without having pre-labeled data. Like if you want to recognize a dog, usually you train a system with a bunch of pictures of different dogs, and hopefully the system learns the interesting correlations, what the tail looks like, things like this. Here, what we're going to do is take an unknown image and do something, a modulation, like a rotation. Or it could be an inversion, it could be different colors. It could be a black, blacking out half of the image. But if we insist that these are the same, the question is, if this image is stored in a bunch of qubits, can we come up with the unitary operation that gives the same output for these two inputs? So you can see it has nothing to do with the dog itself, but the way the dog correlates to its rotation would be unique to the dog. That's the idea. A heuristic, not sure it's going to work in the long run, and it certainly isn't scalable in terms of uploading data into a quantum computer. Again, if you're interested in this, I think I have a reference somewhere. Oh, I did? No. I'm sorry. Yeah, there's a reference on the archive for this one. And it's sort of an algorithm that looks a little like the QAOA that Eddie Fari talked about earlier, where you have parameters that go into a standardized circuit. The circuit doesn't have much structure really, but there's parameters that we classically optimize. And then after many runs of training that classical circuit, hopefully the optimized or the better parameters will give us a recognition of these. Very small system. These are 4 by 4 pixels stored in only 4 qubits. Okay, so finally, the company, building a system where we can pay attention to the entire stack and wanting to improve that system became very expensive. And as it happens, we were approached, Jung Seng and I were approached by venture capitalists, not the other way around. I never really wanted to start a company, but it was clear that this fellow at a particular company wanted to make the bet on quantum. And think that was in 2016. And 5 years later, the company went public remarkably. So it's super fast evolution. And I put a number here blank because it depends on what the stock market is today. But I'll say that number is between, I don't know, it's generally between 5 and 20 market capitalization. This has allowed us to get real engineers, those that work 24/7, I'd like to think, but they're working hard on engineering atomic physics systems. And over the course of time, we've put our systems on the clouds, the servers for quantum computers these days. These are small quantum computers still, even today, but getting people to use them and learn how to learn how to mitigate errors, learn how to compile. This is something that it wasn't obvious that was the right thing to do. In fact, I was kind of unwittingly CEO for about a year in 2019, and that's when the decision came, should we get our system on the Amazon cloud or not? I was actually very negative on it because I didn't want to waste engineering time on a system that would have to run 24/7 and it wouldn't be improving. You can't improve it. You want to keep it where it is, and we wanted to keep improving things. I think I was wrong, and I was convinced otherwise, and I'm glad I was, because by building a system that's so well engineered, we learned so much about how to build the next system and the next, and that's something the physicists generally. I think in physics, my advisor Carl Wyman his approach was make the experiment work, have it hang together just enough to take just barely enough data, and then it falls apart. So it's sort of a different attitude. So I'm going to skip over my component speed slide. Ions and neutrals are slow. The gate speeds are slow, but the architectural time to solution is not necessarily slow. And that's one thing that people miss. Architecture, having full connections, not needing as much error correction is probably much more important than gate speed. So sounds a little defensive, but we're not there yet. We don't have million qubit quantum computers. But when we do, it will play out that we all want faster clock speeds, but architecture is more important. That actually happened in classical computers. I mean, remember when the clock speeds were a few gigahertz? They really haven't changed in a couple of decades. Okay. So what about scaling? I think at the beginning I said that's what we have to do in ions. We definitely need more ions, and we're playing around with full control of 30 or 40 trapped ion qubits right now. And the fidelities are anywhere between 3 nines and almost 5 nines, depending on the system. Not big enough. We definitely want hundreds, thousands, maybe tens of thousands. Brute force approach, I say, and Guido kind of touched on this. These are figures from Luming Duan's group in China and in Beijing. And you can see he had to move the camera. The camera field of view wasn't big enough. You also see there's a lot of defects here. This is actually this has 2 pancake layers. This is a single layer. What is it? 1,000 ions or so. You can see defects for sure. Now, the good news is that if you turn the power off and then you reload these ions, the same defects are in the same place. There are certain magic numbers that are very stable. And so this is not an unreasonable way to get to many hundreds or many thousands of qubits. Now, controlling them is another matter, but at least they're isolated and optically resolvable. Many groups are thinking about this, including Guido's group at Rice. Scaling 1. Scaling 2. This is sort of maybe an obvious one. Quantum systems are rarely naturally qubits. Usually there's many more levels. The barium ion is very interesting. The barium ion, for many reasons, all of the wavelengths are visible. And by the way, all industry now is going to barium, and pretty much this is, I think, trapped ion systems, which is great because neutral atom systems are now going to the UV because they need to make Rydberg levels directly, and it's very hard in high power UV. We're moving away from the UV, and as I'll say later, maybe even moving away from lasers entirely for gates. But barium is interesting partly because of the visible wavelengths are friendly, but also the D levels are very low lying. They're not just low, they're not just below the P, they're way below the P state. That means they have a really long lifetime, like a minute. So these aren't exactly the F states of ytterbium that have 10-year lifetimes or 10,000 years. What's the difference? These have 1 minute lifetimes, which should be sufficient, certainly for error correction to take over. So there are lots of levels here. And Chris Lysenko's group at Waterloo has actually stored a 24 level, I won't call it a qubit, it's a 24 level system. And she's been able to read out every one of those levels with better than 99% efficiency on every one of them. Now, the gates, no, they're not here yet, but what's a 24 level gate look like anyway? So finding more room in the atoms or finding more room outside of the atoms, the phonon vibration degree of freedom in trapped ion strings. Again, Guido touching a lot on what Guido set me up for here, but you have a big boost in the Hilbert space if you can deal with some of these phonon modes. Now, if you have a string of atoms, it turns out you don't want the center of mass mode. It's noisy. It couples to long wavelength electric fields. The electrodes are really far away, but they will produce noise. But that noise has very long wavelength. So the internal modes, the zigzag type modes, are very coherent. They have really good T1s. The T2s are limited by mode drift, just slow voltage drifts. Again, these are technical things, but it's very exciting. Ken Brown and Jungsang Kim are really looking into storing information and actually co-designing to applications that want a bosonic mode, like molecular simulations. So this looks really interesting. Finding more room. I have two more, and then I'll quit. Scaling 3. Shuttling atoms. You can do this with neutrals. That's the main way to scale up neutrals, which again, I haven't talked much about that, is to physically move them around with their laser beams. But of course, ions can be shuttled as well. Dave Wineland and I, Dave Kopinski, kind of put this architecture together, almost 25 years ago to think about shuttling ions around. It's hard because you need a lot of electrodes. They need to be regularized. I would say the company Quantinium has gone the furthest by far in this direction. They now have, I think, sort of a racetrack trap where they have 56 or maybe even more qubits, and they isolate 2 and they do a gate and then they move them back and so forth. Oxford Ionics, which, dramatic drum roll please, which is now part of IONQ, has their own way to scale up by moving atoms around in an architecture that has no lasers for the gates. This will have microwave, or actually more like radio frequency fields that are integrated with the chip to have electronic control of the gates. But the physics is exactly that which we use when we push atoms around. We're pushing them around with microwave gradients. Very clean, and it's this type of architecture that has given us almost 5 nines of fidelity on 2-qubit intake. Okay, scaling 4, which is one of my favorites because I've been working on it for a long time. And again, in PowerPoint, it's easy to think about making a data center. Why not just link each of your ion traps or whatever they are to optical fibers and have a data center where you can spread entanglement through the system? Well, these fibers have to work for single photons, which is actually easy. Photons have very low loss over small distances of fiber. The real hard part, of course, is coherently getting the information from a qubit onto a single photon. It's generally probabilistic, and it's almost always slow. However, it's the only architecture I know that offers full connectivity at scale. You can connect any qubit in QPU1 with any qubit in QPU15 by just changing the configuration of this optical switch. And this is all classical. This stuff exists. So again, the architectural advantages of this may beat the fact that it's really slow. We still want it to be faster. And of course, you can clean up. This is a very simple version of error correction, where if you do it with many in parallel, you can increase the fidelity of one of them. So you're basically making Bell states across a graph of individual atoms. They don't have to be ions, I guess. The nice thing about ions is that they're locally fully connected already through conventional gates. And the way this works, I mentioned, it's probabilistic and slow, and that's because we generally want 2 photons to come from the target atoms. And when 2 photons hit a beam splitter and they're mode matched, they both always go the same way at the outputs, called the Hong-O-Mandel interference. It's a quantum effect. And here you see I'm drawing when both detectors fire and the photons go off in two separate directions. And the reason that can happen is that these photons are produced with two different, say, polarizations. So the photon itself has a qubit, and H and V don't see each other. So whenever you get coincidence counts on these detectors, you know that you had an H and a V, but you don't know which one made H or V. So it turns out when you destroy the photons and detect them, you have announced that these two are in an entangled Bell state. That's very well known by now. The problem is the rate is really low because you have to collect this photon with probability P, and then you have to collect two of them. It's P squared, and P is about 1% right now. So P squared is 10 to the minus 4. The rate at which we can do this cycle is at about 1 megahertz. 1 over 2 tau is about 1 megahertz. So we're talking a few hundred hertz. So that sounds kind of slow. Well, if it sounds slow now, when we started this, it was 10 to the minus 3 hertz. You get one bell pair every 10 minutes. And if you want to take statistics and a curve that shows coherence, you have to take data for a solid week without interruption. That was no fun. But so 200 hertz, I'm happy with that. It's actually encroaching upon the gate speed of intra-QPU gates, the Coulomb-based gates that I spoke on earlier. And when we cross that line, you might say, well, we're not going to cross that line, but hold on. When we cross that line, then the photonic interactions will maybe be more important than the Coulomb interactions. That'll be fun, because now it turns to an optics problem. A lot more integrated optics will be needed. This plot over here is of all the platforms that have done this, and I think I showed a bunch of references that this Hong-Mandel type interference has been performed on pretty much all the optically active qubits. The superconducting work out of ETH was actually microwave photons, but photons are photons. Optical photons are really what we want because we can think about devices. We don't have to be at 4 Kelvin either. So here we have the entangled state fidelity of the Bell pair versus the rate. And obviously, we want to be up and to the right, always up and to the right. Recently, in the last few years, the group from Oxford, not Oxford Ionics, but the University of Oxford, Dave Lucas's group, Chris Balance's group, they were able to get the best in both using a mixed species for sympathetic cooling, but mostly strontium is the workhorse. But we have made America great again in the last couple of years by doing the same thing with barium and ytterbium, the references are down below. Now, this gate speed, it looks like it's not doing so well. And this is sort of why I'm up in Boston a lot these days. IONQ acquired the company called LightSync. And what LightSync does is they work with silicon vacancies in diamond. It's an optically active memory. It's not as good as a trapped ion or a neutral atom, but it's good enough. It has good T1 and T2s. But what's important about SV and diamond is that it couples nearly 100% efficiently to a fiber. That's real black magic. They've been able to glue fibers down. They're tapered fibers, and the evanescent wave couples to this piece of diamond. It has a photonic bandgap cavity, and in the middle of that is a single isolated silicon vacancy that's sort of like an atom. It's one of the cleanest solid state atoms out there. And it's also a different wavelength. It's at 737. So what we're going to do is channel 2 ion photons that come from ions into the silicon vacancy, one and then the other, using this optical switch. Sorry, I kept pointing to this. That's the silicon vacancy. And we're going to have one store its photon in memory while we're waiting for the other one. So P squared becomes P. This is 1%. So this is like a factor of 100 potentially that we can improve. Great. And this is a big collaboration between IONQ and the Duke Quantum Center. Some of my students are up there in the Boston office, hopefully. Okay, let me start to back out. I talked a lot about the photonics here, partly because this photonic idea, having an architecture that's connected in this fully connected graph, is why IONQ started. It wouldn't be a company without that scalable plan. And this is the venture capitalist, Harry Weller, and he literally had this phys rev A paper in his hands when he visited me, and he said, this reads like a business plan. over the course of a couple of years, convinced us to go ahead and try to start the company. And I'm heartened to say that finally we're at IONQ really going strong after these optical interconnects so that we can hopefully, scale in a modular way to utility. So I think this is my last slide. Another business, you see this in business books and so forth. A new technology has something called a hype cycle, where the expectations over time can be kind of outlandish. But we should all remember that these technologies, and this could be flash memory, digital cameras, could be almost any technology you want, hard drives back in the day. In the long run, they are useful. Matter of getting there. And if you overhype it, people worry that the investment will shrink, people will be disillusioned, and then everybody loses. And you want to avoid that. And the academic side in me sort of sees maybe a way out. I don't know how much voice we have in industry, but we're already using these quantum systems. You can call them fully blown quantum computers if you want, or quantum simulators, and they've been featured here at this meeting. They're used right now for science. Now, that's not a business, and it shouldn't be a business. It's okay, but it keeps the word out there. So while I poke fun at the big companies because I don't think they know what they're doing with their chips, they're owed a great deal of credit for really opening up this field and making everybody pay attention to it. I think we're going to need both academics and industrial players if we hope to really make headway. And I think maybe there's something in the middle that should be refined to do this. I'm not convinced it's a DOE lab, maybe, but maybe there's something else that's funded by industry, maybe philanthropy, but maybe not a university either. Hire staff over the long term and have professional engineers that want to engineer a quantum system. So with that, I will put my cheap ad for the Duke Quantum Center, which is sort of we fashion ourselves as not a physics center, but one that uses our machines to do all kinds of things, not just physics. But we're, of course, it's not just ions either. Han-Chun Lo and Travis Nicholson had recently joined us, and they're building a Pittsburgh atom array and a strontium experiment as well. But all of the hardware we have at Duke, they're optically active quantum systems, because we do believe that the integrated optics and the devices that are already coming through classical computers and data centers are really what's going to allow us to scale in the modular way. Good, thank you.
So you mentioned commercial optical switch for scaling connected quantum computers. Obviously, it depends on the quantum encoding modality, but for example, polarization is going to be completely destroyed by existing commercial switch, as far as I know, at least. Or if you go, for example, time being, you need to be a really deterministic jitter in your switching. Otherwise, again, your encoding goes out of window. So I want to see what's your comment on that. Yeah.
Okay. So the question is about this switch here. There it is. See, I just drew it. Just stole a picture. Actually, Jungsang Kim, the co-founder of IONQ, when he was at Bell Labs 25 years ago, he was on the Lambda router project, which aimed to, it was a 1,000 by 1,000. So 1,000 input fibers, 1,000 output fibers. And you should imagine an imaginary operator, telephone operator, that's connecting any pairs of fibers that are asked for. And this is done with MEMS mirrors that would redirect. So it goes into free space, MEMS mirrors, and 2 banks of MEMS mirrors. So that's 4,000 MEMS mirrors, 4,000 axes, 4,000 high voltage supplies that go with it. This is a $400 million project that Bell Labs abandoned because longitudinal multiplexing was so efficient. You don't want to go into free space if you don't have to. So these switches exist, and at least the MEMS mirror version will, I think, preserve polarization. I don't know to how many dBs, maybe to 0.2 dBs. However, we're thinking time bin. We're certainly thinking time bin. And we've already, another nice thing about time bin is it's not limited to just 2 states. You can couple the multi-level qubits to like five time bins or something. And the same Hongwu Mandel thing works with time bin qubits, polarization qubits. Frequency qubits are very interesting because the frequencies of this decay, almost, right? Yeah, that's the slide I want. You'll see that these two branches of the decay have slightly different frequencies. They're resolvable. They can be different by 10 gigahertz. And again, because the bandwidth of each photon is only a few megahertz, 10 megahertz compared to 10 gigahertz, they're resolvable, and you can also use the frequency degree of freedom. Yeah. Question. We have to think about these high-level design issues. And
my name's Aaron. I'm with the Pennsylvania Quantum Public Lobby Group, and we're working with lawmakers to try to get a state plan to build and utilize these technologies. IONQ has worked with a lot of states so far to build plans to build and utilize like the workforce and a lot of the different components to these industries. How can we successfully lobby the state government to craft a plan of our own in Pennsylvania?
Good question. Yeah, there are a lot of states that have really been ahead of things. A lot of it has to do with the personality of the states. I think Illinois and Maryland, Texas is sort of coming on strong now. But Illinois and Maryland have very well-connected governors who are kind of go-getters. I think if you can have personal interactions like at that high of a level and get them sort of infected with the quantum bug, that's great. But I think you're more interested in how that'll affect, say, 10 years down the line, the workforce in Pittsburgh or Philadelphia and throughout the state. You have great universities and great place for businesses to thrive. I would think you're even better set up than Illinois.
Thank you.
So I didn't answer your question. I mean, I think having people at your universities that can get a high level to say the governor is I think showing graphs of all the public money throughout the world going into quantum, how it's growing and how industry is playing a huge role. Nancy, state, Pennsylvania. Good arguments. I mean, play the card. Well, we have to. If Illinois and Maryland are doing it, we have to do it. That does work. I don't like to play that card so much. In Congress, we hear that about China. Just say China to a congressman, and they'll say, "Oh God, we have to have the National Quantum Initiative." There's some truth to that, but yeah.
Hi, my name is Jay Kim. I'm a machine learning engineer for a company based out of California. So you mentioned that Silicon Valley doesn't necessarily have everything it takes to get into quantum. Do you think that they'll bring their software skills and prowess eventually? Do you have an estimate upon when they'll bring their full force on and start applying machine learning models onto quantum computers? Because that's what I currently play around with.
I don't know if I ever said that Silicon Valley won't play a big role. Maybe I was picking on the big companies, but
Yeah,
I
sorry.
think there will be a new set of big companies.
Okay.
And maybe I think what's great about Silicon Valley is that it's the workforce there and non-compete laws that are hard written in the state are really conducive to tech. It's already there, and people like you and these are the people we need in this field. Start thinking about programming a different type of architecture. So I would be surprised if Silicon Valley doesn't play a big role in that.
Okay. Thank you so much.
Okay, if there's no more questions, let's thank Chris one more time, please. Two announcements. One, the black, dare I say, iconic PQI mugs that are on the tables are yours for the taking, so you can fight over those. And then the second thing is, please join us for the poster session and refreshments downstairs. free drinks, free food, and free science. So see you there.